Okay, so we were building some mathematical stuff regarding CODECS. So let me give a couple of examples. So basically, I will formally now tell what is error correcting code, especially linear code, and how it is used for encoding and how it is used for decoding, and some very basic example about dual code and petty check matrix and so on, so in the generator matrix. Okay, so I'm going to take the same example. C is equal to 0000111. So I think you already saw all this stuff here. Let me rewrite for you. So if we have if we consider the space, I am looking at only binary space right now for simplicity. This is the binary vector space having 2 raised power n elements. So a code is, so basically this is nothing but set of all tuples x1, x2, xn such that xi belongs to Z2. So this is our space, which is n-dimensional space. And from this n-dimensional space, what is the definition of code? A code is simply a subset of Z2n. Subset means just we are taking certain binary strings and that will act as a code for us. So formally, we define it with NMD. There are 3 parameters. N is known as length. M is nothing but size of C, total number of code words, and D is minimum Hamming distance. Okay. So when we say subset means if I take X and Y in C, this will imply need not be that X plus Y may not belong to C. If we simply take a subset, right? So such kind of code is known as non-linear code. Okay. So a non-linear code is just bunch of binary strings, right? And these binary strings are used for error correction based on this property of Hamming distance. Now, in case of a linear code, C is nothing but k-dimensional subspace. And then we denote it by, so linear means, then we call it as a linear code. That means if X and Y belongs to C, this implies that X plus Y also belongs to C. If we take 2 vectors, its sum will also be in the C. And there we denote it by N, K, D. N is length, K is known as dimension, and D is minimum Hamming distance. Okay. So these are some basic notations. So a code is nothing but simply a collection of binary strings of length n, and we denote it by small n, capital M, and small d. Small n is the length, capital M is size of C, total number of code words or vectors in C, and D is the minimum Hamming distance. So this kind of arrangement is known as non-linear code. If it turns out that if I take any 2 vectors X and Y in C and their sum is also in C, actually it's a linear code. And in fact, in that case, C is nothing but a k-dimensional subspace of Z2n. Z2n is an n-dimensional vector space, and C is nothing but a k-dimensional subspace of Z2n. And then we denote it by n, k, d. Small n, small k, small d. Small n is the length. Okay. Small k is the dimension of the space, and D is the minimum Hamming distance among all code words, right? These are the basic parameters. So that means the linear code that we took earlier, sorry, I'll take it to the next. So that means when we take C is equal to 0, 0, 0, 1, 1, 1, this code is nothing but subspace of Z2, 3. Subspace. And one dimension subspace. Cardinality of C is 2 raised to power 1. Right. So this repetition code that we used is nothing but a one dimensional subspace of this. Okay. As I mentioned, so basically, given a code, suppose we are taking, suppose we are having a linear code. A linear code is given to us. Now, since it is a k-dimensional subspace, it is described by two kind of matrices. One is known as generator matrix, consisting of all the basis element, okay, which can generate the whole space. So it can be described by G and it can be described by H. H is known as parity check matrix. I'll talk about it in a minute. But G is known as generator matrix. Okay. So for example, this C, G is nothing but 1, 1, 1. 1 cross 3. Okay. So only having one row because it's a one dimension. So in general, G is K cross N. K rows, N columns. Why? It's because it's a K dimension. That means a basis will have, the basis set of this space will have K vectors, which are linearly independent and they span the whole space, right? So standard notation is G is equal to IK and A. For some matrix A, IK is the identity matrix, K by K identity matrix. So this matrix is standard form of the generator matrix. We can always do this because the basis has all linearly independent vectors, right? So we can take the natural choice towards the beginning by doing certain row operations so that the identity matrix will appear at the beginning, right? So this is IK. This will ensure that all these rows are linearly independent, right? Okay. So this is the standard form of the generator matrix. Once we have this G, so for example, here G is 1, 1, 1, right? So this generates both the two vectors 0, 0, 0, 1, 1, 1, right? Now, before describing H, I would like to talk about what is known as dual space. Okay. Yes. Sorry. Huh? Yeah. I am going to talk about it. Is there 1001 is there? I2. No, so basically vectors are linearly independent. You can check the vectors are linearly independent. Lambda 1 times first vector plus lambda 2 times second vector. Take the linear combination, put it equal to 0. All scalars will be 0. Okay. So let us take. So we define what is known as dual space. It is all those vectors y in. I'm just taking binary space here, such that inner product of s comma y is equal to 0 for all x in C. For a given space C, I can define its dual space, which is all those vectors in the whole space, which has inner product 0, which are orthogonal to all the vectors in C. So in order to understand this, let us take an example. Suppose C is 0, 0, 0, 1, 1, 1, right? And now I can write down what is Z23. Z23 will be 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. All 8 vectors are here of the whole space and C is given to us. Now our job is to find out C perp. Can we do it now? So what we need to do basically, C perp will be all those vectors in the whole space which are orthogonal to every vector here. Okay, so I'm going to start with 0, 0, 0, the first vector. Is it orthogonal to the 0, 0, 0? Yes, because the inner product will be 0. 0, 0, 0 vector will have inner product. Inner product is defined as, so inner product of x comma y is x1 y1 plus x2 y2 plus x3 y3 dot 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 xn yn, right? Mod 2, right? That's a very basic thing. So that means first vector is first vector will be 0, 0, 0, right? I took 0, 0, 0, I computed the inner product with each vector in C and in turns out the inner product is 0. So that is there. What about this second vector 1, 0, 0? Will it belong to C perp? Now 1, 0, 0, the inner product with 0, 0, 0 will be 0, fine. But what about with inner product with 1, 1, 1? So 1, 1, 1, it will be, inner product will be 1, which is not equal to 0. So this is not going to work for us, right? This is not going to work for us, right? Go to the next one. Everything is modulo 2. You need to keep in mind that everything is in modulo 2. Take the second vector 0, 1, 0. Again, this is not going to work. Third vector 0, 0, 1. That is also not going to work. What about 1, 1, 0? 1, 1, 0 has inner product with 0, 0, 0, which is 0. And also with 1, 1, 1, it is 0, right? So this is going to work for us. 1, 1, 0. What about the next one? 1, 0, 1. That is also going to work. And 0, 1, 1. This is also going to. What about triple 1? Triple 1 is not going to work, right? Right? So I have just shown you an example. Given a vector space, C, how to find its dual. I think you know all these things. I'm just doing an example so that you are able to recall. Right? So now you can clearly see that. What is the dimension of C? 1. Because general matrix has only one element, right? One vector, 1, 1, 1. What is the dimension here? 2, right? Because there are two linearly independent vectors. I can take either this or this or this or this or this or this. Any of two out of this will work as a basis for this space, right? Take those two vectors, take the linear combinations lambda 1 times first vector plus lambda 2 times second vector, such that lambda is a 0 or 1. You get all the 4 vectors. Right? So dimension here is. So we know that dimension of C is 1 and dimension of C perp is 2, right? In fact, you can see that dimension of C plus dimension of C perp is equal to 3, which is n actually in general, right? So dimension of C perp is n minus k always, right? You can clearly see that. Huh? Yeah, so you can take any two. I mean, you suppose you take these two vectors, middle one, they are going to work as a basis, right? They are linearly dependent or independent? How can they are dependent? So if you take lambda 1 times this plus lambda 2 times this, put it equal to 0, what happens to lambda 1 and lambda 2? Can you write down, in other words, can you write down this vector as a linear combination of this vector for some lambda? Which is lambda is 0 or 1? Not possible. So they are linearly independent, right? Okay. You take any two vectors, they are linearly independent. So two vectors are linearly dependent if one vector is lambda times the other vector for some scalar lambda, right? Okay. So this is what is, they are independent. Similarly, you take any two, they are independent actually. Right? Out of these three non-zero vectors, take any two, they are independent, right? So that means generator matrix will have two vectors only, right? Got it? And so this is the famous theorem. So dimension of C per B is always n minus k. Right? You can clearly see the dual space. Right? Okay. Now I am going to give you some idea about parity check matrix, which is very, very important. So remember, so a linear code is nothing but a k-dimensional subspace, right? And so it is, the parameters are small n, small k, small d. Small n is the length, k is the dimension of the space, and d is the minimum Hamming distance, right? So based on d, if d is very large, you can correct a lot of errors, right? I mean, that is what is possible. So the question is, now this space can be described by the generator matrix. I showed you the standard form of the generator matrix. G is equal to IK and A, right? This is the standard form of the generator matrix. Now, actually, so first of all, let me, okay, I will just again recall, how do you encode the data using this generator matrix? So now encoding is possible in two ways. Number one, so suppose we have k bits. K bits are given to us. I want to encode them, right? So you multiply with G, which is k cross n, and you will get, say, y1, yn, n bits. So basically, this is one row k column. K bits multiplied by G gives you n bits. This is how you do the encoding all the time, right? Through generator matrix. Okay? K bits are there. I want to encode them. So basically what we are doing, we are extending k bits to n bits, such that, you know these n bits, basically, so k bits are multiplied with the generator matrix G, which is k by n, gives you. So I think in case of 0, 0, 0, 1, 1, 1, you remember, if you take this matrix and I want to encode 0, so 0 into this is 0, 0, 0, 1 into this is 1, 1, 1, right? So 0 encoded as 0, 0, 0, 1 is encoded as 1, 1, 1, right? This is a very straightforward encoding method. Okay. There is another way of interesting method of encoding through parity check matrix. So let me give you a brief idea about parity check matrix. How do you find A matrix? So basically basis, right? G is nothing but the basis elements. If there is a vector space, so this is the vector space. For example, if you go to the next one, here you see, suppose this is a vector space C, right? So generator matrix is what? 1, 1, 1, right? So capital A is what? 1, 1 there, right? Whatever it is, the basis elements that are coming, right? Okay. Now another interesting thing is this. Suppose I have k bits. Now I am going to tell you what is parity check matrix definition. So one way of encoding is take k bits, multiply with the generator matrix G, and you get n bits, right? That's encoding. Another way is that I am taking k bits. Now I am adding extra n minus k bits. I am adding extra n minus k bits. These are n minus k bits, right? These are the info bits, I would call it. Initial k bits are there. I am adding extra n minus k bits such that Hx transpose is equal to 0, where this is nothing but our vector x. For some matrix H. And this matrix is then call it as parity check matrix. So what is the definition? K bits are there. This is another way of encoding. K bits are there. I'm adding extra n minus k bits such that hx transpose. So this is the row vector, right? So if you take the column vector, right? So basically, x transpose is a column vector, right? Multiply with h for some matrix H. So what is the size of H actually? H is of size n minus k cross n. N minus k rows and n columns, right? You multiply this with x transpose. So hx transpose turns out to be 0. So essentially, given k bits, I am adding extra n minus k bits such that this whole vector is a member of, so basically it's a member of this null space of H for some matrix H. So then such kind of matrix is known as parity check matrix. The question is, how do we find it? I'm going to tell you now, right? Actually, this parity check matrix also describes in a very natural way the space, our linear code. So linear code parameters were n, k, d, right? K-dimensional subspace, right? That can also be described by this parity check matrix. So let me show you those relationships. So first of all, so if C is our NKD, right? Then suppose generator matrix is IKA. This is K cross N. For some matrix A, which is binary matrix A, right? Then it's parity check matrix H. This is our generator matrix. So its parity check matrix H is minus A transpose I n minus k. Okay, if it is too much, I can write it like minus A transpose. So this is n minus k cross n. If generator matrix is given in this form, standard form, the standard form of H is this, which is the parity check matrix. I'll show you the relationship. So basically, you can check that GH transpose is equal to 0. So it turns out that if you take C, look at the dual space, the generator matrix of the dual space is nothing but the parity check matrix. Okay, so these are relationship, interesting relationship in terms of vector spaces. Okay, so minute. Okay, so now let me take an example. Okay, if I take an example, G is equal to 1011. G is equal to 1011 and I guess 0101. This is our 2 cross 4. Cross 4, right? So I can see that it is I2 slash A. What is A is 1101. Standard generator matrix. I have to ask to find H. What will be the H now? H will be in this case minus A transpose. Minus is same thing as plus modulo 2. So A transpose will be 1011, right? Minus A transpose and then I2. This is our H matrix. Okay, 2 cross 4. n minus k across. So given G, I can find H. Okay? By this formula. Of course, there is a proof for this formula, but I am skipping that proof, but can be done. So given G, I can find H like this, minus A transpose I n minus K. Okay? I have shown you. Now I will show you actually. So take this code and so I will show you that this code generated by G can also be obtained through this H. Okay? Let me show you how. So if G is 1011 0101, right? I hope that is the same. Yeah. Okay. So what will be the C? C will be the linear combination of these two vectors, right? These are the 2 cross 4. So this will be, I can write it down as lambda 1 times 1011 plus lambda 2 times 0101 such that lambda 1 lambda 2 belongs to Z2, right? This is our C. Because this is the generator matrix, right? These are the basis elements of the space. So that means, obviously, you can see that 0, 0, 0, 0 will one vector, 1, 0, 1, 1 will be another vector, 0, 1, 0, 1 will be another vector, and okay, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, and then we have 1, 1, 1, 0. Do you agree? These are the all vectors you will get by taking lambda 1 and lambda 2 as 0 or 1, right? Essentially, what we are doing, I am taking the first 0 vector, take these two vectors, one vector is left, which will be the sum of the two. Just modulo 2. Bitwise modulo 2 is there, right? Operation. So you get all these 4 vectors, right? One zero one one zero 1011. Okay. Okay. So the question is now, let us take the H and try to see if we can find the same C or not. So H is given to us. If G is this, what is H? We have just obtained, 1010 1101. This is our Petri check matrix, right? Okay, this is the Petri check matrix from the formula we obtained, right? If G is IK A, H is minus A transpose IN minus K, right? This is how we got the Petri. Now, from H, you see what is the definition of C? It's a null space of H, means all those vectors X such that HX transpose is equal to 0. That's the definition I gave it to you, right? So let me see. I want to check whether C is basically all those vectors X such that HX transpose is equal to 0. Right. I want to find these vectors X such that HX transpose is equal to 0 and see what happens. If we are getting C, then everything is fine, right? So what we need to do, H is given. What we need to find, all those vectors X. So X is unknown, right? So I can call it X is equal to X1, X2, X3, X4, right? Which is fine. So I'm calling it. So essentially, we are getting HX transpose 1010 1101 X1, X2, X3, X4. Right? I'm just writing HX transpose. This is H. X transpose as a column vector. X1, X2, X3, X4, right? Now I can just multiply. That means what? X1 plus X3 is equal to 0. Right? When you multiply, This will give us x1 plus x3 is equal to 0. And second one, we are going to get x1 plus x2 plus x4 is equal to 0. Do you agree? I want to find x. For what x this will happen? So I'm just multiplying. H x transpose is equal to 0. That means we are getting these two equations. Obviously, there are, some of these unknowns. I need to take arbitrary, right? Because if you want to find solution. So what is, so I can say that x3 is nothing but minus x1. Minus the same thing as plus. So x3 is equal to x1. Okay. So from this, I can say that x3 is equal to minus x1 is equal to x1. Now x1 I can choose 0 or 1 and I can find the value of x3. So x3 is known. So x1 is known, right? x1 is known, that means right from there x3. So basically, sorry, x1 is arbitrary assigned, right? Now here also I can say that x4 is nothing but minus x1 minus x2. Same thing as x1 plus x2. Right. So x1 is arbitrary assigned. x2 is also arbitrary assigned, right? So x4 is nothing but this. These two equations we got. So we got x3 is equal to x1. So x1 is arbitrary, x2 is arbitrary, x3 is equal to x1, and x4 is equal to x1 plus x2. Now can I find all the values of xi's? By varying x1 and x2. So x1 and x2, there are four possibilities: 0, 0, 0, 1, 1, 0, 1, 1. Can you just see what are the values of the other values you are getting? If you take x1 to be, so basically I should say that here I can make a table kind of thing. x1 is 0, x2 is 0. Then x3 is what? 0. And x4 is what? 0. So you get first vector here. Are you getting all these four vectors? You can check. Are you getting all these four vectors here? Right? When both are 0, when x1 is 0, x2 is 0, x3 is also 0, x4 is also 0. You are getting this vector. Fine. Right. Now when x1 is 1 and x2 is 0. When x1 is 1, so x3 is 1. Right? Which vector you are getting? Second or third? Third. Are you getting what is happening? Okay. Solve calculations, right? So basically, I'm saying that I'm just plugging the values. There are two equations, important equations. One is this one, another one is this one. I have to vary the values of x1 and x2 and find out the values of x3 and x4. Okay. These are the possible values for x1 and x2, arbitrary values. Right? Okay, so first vector you are getting 0, 0, 0, 0. Second vector you are getting third 0, 1, 0, 1, and fourth is 1, 1, 1, 0. See the beauty? From this H you are getting the whole thing. लोग कैसे सोचते हैं इसके बारे में? That's interesting thing, right? Getting the same C. So this is the story of parity check matrix essentially. Okay, so I hope you got this this C from H. Okay, so that means given a subspace, k-dimensional subspace, it can be described by two matrices. Either you describe it by parity check matrix H or the generator matrix G. And these two matrices G and H are such that G into H transpose is equal to 0. They are orthogonal, which you can verify as a T type problem, right? G into H transpose is equal to 0. Right? So this condition is there. Right? G into H transpose is equal to 0. Interesting thing. So now I talked about some of the basic stuff. Now I can tell you something about the decoding. See, uh, first of all, so encoding is straightforward. How do you encode? If there are k bits given to you, so you basically encode those k bits into n bits by multiplying by a generator matrix G, which is k by n, and you are done. That is one approach. Another approach is basically take k bits, add extra n minus k bits such that hx transpose is equal to 0 for some h. Both will do the encoding part. Okay. Huh? Yeah. So encoding, there are two ways, and I'll show you why h is beautiful thing. In a minute, when you do the decoding actually, right? So given a linear code, which is k-dimensional subspace of a vector space, right? It can be described by two kind of matrices, generator matrix and parity check matrix, and both these matrices can be used for encoding the data. K bits into n bits. Okay. One way is k bits multiply with G, you get n bits. That is one way. Second is take k bits, add extra n minus k bits such that hx transpose is equal to 0 for some h, right? So this is the thing. Now, when we want to decode it, see, remember that example of the repetition code, what you know. Yeah. So this repetition code, you remember, we use this idea of the Hamming distance, right? You send something from here, say 1, 1, 1, you receive a vector which will with error, some bit is flipped, and you compare this received vector with this and compute the Hamming distance, and you do the calculation, right? So the whole process can also, you can think of what is known as sphere decoding, and that's something really interesting. So what you can do is the following. Yeah. So take this code C, just write down, and now what you do, draw a sphere of radius t for each x in C. There are two vectors here, 0, 0, 0, 1, 1, 1. And what is the definition of the sphere? All those vectors y in Z2, 3, such that distance between y comma x is less than or equal to t. So what are these values here? S1, 0, 0, 0, if t is equal to 1. So you need to look at, so Z2, 3 has 8 vectors. Find out those vectors which are having distance 1 from 0, 0, 0. What are these vectors here? I can write it down, the values of Z2. So what I am doing, I am taking the subspace C, I am taking a vector x in C, and for each vector I have to do this. Take an arbitrary vector x in C, draw a sphere of radius t, where t is greatest integer d minus 1 by 2. D is the Hamming distance. Okay, and then you see what happens. So what are the vectors that are going to come here? 0, 0, 0 is the center. So essentially I am saying that from 0, 0, 0, what are the vectors which are at distance 1 from this? This, right? And of course 0, 0, 0 will be part of it. So I can write down all these 4 vectors here. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Right. What about the second one? Now, if it, so this is the first vector I have taken, x equal to 0, 0, 0. I am getting this sphere, vectors in the sphere. Now I take the second vector, 1, 1, 1, and distance 1. What are the vectors with distance 1 with from 1, 1, 1? Huh? So it will be obviously 1, 1, 1, which will be distance 0. Then 1, 1, 0, 1, 0, 1, 0, 1, 1. Right? Right? So that means I have taken the vectors of C, draw a sphere of radius T. What is T? Greatest integer D minus 1 by 2. Here D was what? 3. Distance was 3 in this code. Right? So D minus 1 by 2 is 1. So T is equal to 1. This value of T is 1. So I have drawn a sphere of radius 1. And now the beauty, you see the beautiful thing. Whole space is divided into these two spheres. Union of these two spheres is the whole space. Now this technique can be used, in fact, much more than that, because these spheres are disjoint. Number one property. These spheres are disjoint. They have no vector common. Beautiful property. Second, obviously in this case, in this specific case, I would say that union of these two spheres will give you the whole space. They are decomposing the whole thing. Now what happens? Suppose you send 1, 1, 1. I'll show you in a very different manner how do you decode. Suppose you send 1, 1, 1 and error happened and you received 1, 1, 0. Now this 1, 1, 0 will fall into one of these spheres only. Right? Either this or that. You see which sphere it is. 1, 1, 0 is in this sphere. So the decoding will be the center of the vector, center of the sphere is the actual vector that was sent. Right? Because all 1 bit error from this are within this sphere only, right? So if you send something, right, 1 bit error happened, you can see that it is in this, it cannot escape the sphere. 1 bit error means the distance is 1, right, between the two vectors, right? So the whole idea of calculating the distance, now you can think in terms of a sphere. Just draw the spheres and see. So if you take say 0, 0, 0 and 1 bit is there in the error, so you suppose you receive 1, 0, 0, 1, 0, 0 is in that sphere. So the decoding will give you the center is the decoded part, right? So this is known as sphere decoding, okay? Sphere decoding, right? Any question? Yes. If disjoint is not there, there will be a problem. And this is the property you can prove that, again, T time problem, that these spheres are always disjoint. Okay, this is the beauty. Okay, so that's why we are able to see the beautiful math can be used to correct the errors, right? So basically these spheres are always disjoint, right? So you, no matter what vector you send, if it falls in, if error happen, right? So suppose T errors happen, T bits are flipped. So it will be in the sphere centered at actual vector, which is distance T apart from that, right? So in somewhere in that sphere it will be there, right? You can actually do that, okay? So I think that's all for today. So I will talk more about decoding and we'll finish the decoding in the next, okay?